Hello, I'm Zhiyuan from École Polytechnique and Cisco Systems France. I will briefly present our paper, Learning Distributed and Fair Policies for Network Load Balancing as Markov Potential Game in NeurIPS 2022. First, let me introduce the network load balancing problem in data center networks. On receipt of a new request, for instance a SQL query, the load balancer needs to decide which server will handle the new request. Decisions could be made based on the queue length on the servers. However, servers can have different processing capacities, which is an unknown information for the load balancer. So to improve the quality of service and resource utilization in an elastic and dynamic networking environment, a reinforcement learning-based load balancing algorithm, RLBSAC, was proposed last year to make better workload distribution decisions. However, RLBSAC is evaluated on simulators instead of on real-world systems, and it focused mainly on single-agent scenarios, while in real-world systems, multiple load balancer agents are deployed to avoid single point of failure, which can directly lead to the problem of partial observations. For instance, when there's only a single load balancer agent, it has global observation on the server queue length. However, when traffic is split among two load balancers deployed in the system, each load balancer has only a partial observation. And in this case, the load balancer on the top will mistakenly consider that the circled server is less loaded, while in reality, it is the most utilized server. So to understand the load balancing problem, we study a queuing model where we define M load balancers and N servers, with the workload assigned to each server, whose processing speed can be different. We can derive the expected time to finish for all the workload on a given server. For instance, given timestamp Tn, we can get the highlighted part as the expected time to finish for server 0 and server 1. Then our objective is to find the optimal policy that minimizes the cost function C given all the server load states. The cost function is conventionally defined as the make span, or the max server load state in the system. So this is a theoretical model, but in real-world systems, what are the additional constraints? First, network load balancers operate at the transport layer and do not have application-level information. Thus, no make span can be computed on network load balancers. Instead, we can only rely on the limited observations, namely the number of ongoing jobs and the distribution of job durations. Second, in the context of networking environments, the workload follows long-tail distribution, and the traffic rates can be quite bursty. Make span fails under these scenarios. For instance, the two different cases yield the same make span, which make span a less desirable reward for reinforcement learning models. Therefore, we propose to use a variance-based fairness index to evaluate the overall workload distribution in the system. Third, we've discussed about the problem of multiple agents and partial observations. Centralized training and distributed execution algorithms have been proposed to tackle these issues. However, in networking systems in production, they can incur significant communication overhead, especially in large-scale data center networks. Therefore, we prefer to build independent agents which can cooperate to achieve pure Nash equilibrium based on only local information. And this is the charm of the Markov potential game, where we have proved that the variance-based fairness index satisfies the requirements as a potential function. And the proposed multi-agent reinforcement learning framework that we implemented in the real-world system is shown in this figure. We extract networking features from the data plane so that the reinforcement learning agents are able to infer server load states in real time and make informed load balancing decisions to optimize the performance. More details about this workflow can be found in our paper. Experimental results show that our distributed multi-agent reinforcement learning framework using the variance-based fairness as rewards converges and effectively achieves better load balancing performance. And we have shown that our method is the new state-of-the-art in terms of quality of service than existing load balancing algorithms and CTDE reinforcement learning algorithms. And in our paper, you will find more in-depth evaluations with respect to reward engineering, the evaluation of Nash equilibrium gap, scalability and robustness of the proposed load balancing algorithm, and communication overheads. And this concludes my brief presentation of our paper. Thank you.